This is my Calculus 1 course. Today we're going to use the chain rule along with the product rule and the quotient rule. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. So you probably noticed by now that you're expected to know the exponent rules in this course. If you want to have these right in front of you, take a picture. You'll be expected to know those rules for the rest of your math education. And be sure to have these differentiation formulas in front of you. You'll need these throughout this class. So in the previous class we learned the chain rule, and now we're going to use it with the product rule, and then we'll use it with the quotient rule. Now, as I mentioned in the previous class, students typically have a lot of trouble with the chain rule. That's very common, and so I mentioned that the only way to deal with that is just to do more practice problems. So we're going to do some more practice problems with the chain rule, but we're also going to, again, review the product rule and the quotient rule. And of course, we're also going to review the other rules, the power rule, the constant multiple rule, the constant rule, the sum rule, the difference rule. Basically, we're going to do every single differentiation rule that we've learned so far. So you see we have a product, a blue expression multiplied by a yellow expression. And so if we want to find the derivative, we have to use the product rule. And again, you should have that right in front of you. What is the product rule? It says that if you have a product and you want to find the derivative of that product, then the derivative is the derivative of the first expression in the product multiplied by the second expression in the product plus the first expression in the product multiplied by the derivative of the second expression in the product. That's the product rule. Now, again, I know that that's annoying. I know that's weird, and we prefer to not have to do that, but that's just the way that these derivatives work. So we're going to find the derivative of the first expression in the product and then multiply that by the second expression in the product. Then we're going to add the first expression in the product multiplied by the derivative of the second expression in the product. Okay, so you don't have to write d over dx. You can just find the derivative and do it in your head. And again, the reason we use brackets is because we don't want to confuse this green expression as something inside the derivative notation there. We don't want to think that we're finding the derivative of this. But it's not a problem over here because this d over dx is considered to be separate from the x cubed. So we have 3x squared. That turned into that. And the derivative of cosine 5x to the fourth, well, we have to use the chain rule because we have a function inside another function. So the derivative of the outside function, derivative of cosine, is negative sine. So that's step number 1 of the chain rule. Step number 2, keep the inside portion. So step number 1, step number 2. So we kept the inside portion. Maybe I can use brackets here to make things a little easier to see. And then we're going to multiply by the derivative of the inside function. That's the chain rule. So all of this red stuff turned into this. So now we just have to simplify and we're done. So we have 3x squared cosine of 5x to the 4th power. And I guess we can go ahead and just write minus, because we know it's going to be a negative. Negative x cubed sine of 5x to the 4th power, and then the derivative of 5x to the 4th is 20x cubed, and we have to be careful not to confuse this as being part of the inside of the sine function. So in order to deal with that, we should probably write brackets or something. So that's where that came from. And then we can write our final answer. And if you notice, we used a lot of differentiation formulas. A lot of differentiation formulas. We'll count exactly how many we used. And of course we combined these, multiplied. So looks like that's it. That's all we can do to simplify that. So we used the product rule, obviously. That was up here. And we had to use the power rule here. And we had to use a rule where we found the derivative of a trigonometric function. And we used the constant multiple rule over here. I don't think we found any derivatives of constants, so we didn't use rule number 1. I don't think we used rule number 4 or 5. Let's see, but we did use rule number 8, the chain rule. So in one problem, we used this rule, this rule, this rule, and this rule, all in one problem. Okay, so let's try another problem. We have a product here of one expression times another expression. And so we have to use the product rule if we're going to find the derivative. So what does the product rule say? It says we find the derivative of the first expression, and I guess you can use brackets. Probably don't need brackets in this case, but I'm just going to write them just to avoid any confusion whatsoever. Well, I'll try to reduce confusion. So the derivative of the first expression times the second expression. Actually, now that I think about it, brackets are probably not going to work. We have to use brackets on the outside, so we can just use parentheses, I guess. You probably don't need these green parentheses here. You could probably just leave them off, but you know, it's up to you. But you do need the brackets if you're going to write it in this. If you write the x squared first, which you can do, then you don't need brackets. But the formula is easier to memorize, I think, if we do it this way. Okay, so now we're going to add the product of the first expression times the derivative of the second expression. So again, that is the product rule. Let's just double check, make sure we did everything correctly, everything looks right. So now we're going to find the derivative of this expression here, but we have to use the chain rule because we have a function. Well, I'm going to use blue. We have a function inside another function. So we do have to use a chain rule. So I'm going to find the derivative of the outside while keeping the inside. So the green is a derivative of the outside, and I kept the inside. And then I'm going to multiply by the derivative of the inside. That's the chain rule. That's how you find the derivative of a composite function. A composite function, remember, is a function inside another function. So I'm going to have to use brackets around this. And then we're multiplying by x squared. If you just put the x squared next to this, that's kind of dangerous, because you don't want to think you're finding the derivative of this product. So then we have 3x squared plus 2 raised to the 4th power. And the derivative of x squared obviously is just 2x. So that became that. Okay, so now we just have to find the purple derivative. So we have 4 times 3x squared plus 2 to the 3rd power. The purple derivative is 6x. And then we're multiplying all that by x squared. And then we have 2x times 3x squared plus 2 raised to the 4th. Now you might ask, do we have to move this over here? You don't have to, but it just looks better to move it into the front. That's traditionally what's done. Okay, so now we're going to multiply all of this by 4. So we get 24x cubed. We're going to keep the 3x squared plus 2 raised to the 3rd power. We're not going to do anything with this, because if we did, that would just make the expression look more complicated. And then we're going to rewrite the expression over there. And so there you go. So those were 2 examples where we used the chain rule with the product rule. So first we had to think about the product rule, because we had a product, right? So look at the red. See the red expression? And then we had to multiply by the pink expression there. Okay, now look down here. You see the red expression down there? We multiplied that by the pink expression, so that's why we use the product rule. But then while we were using the product rule, we saw this function inside the function. You see the green down here and up here? We had functions within functions. So as we used the product rule, we also had to use the chain rule. And I know what you're thinking. You're thinking, why are you making my life so difficult? But these are just the type of things that you have to do in the calculus curriculum. You can't escape all this algebra. This is really the main objective of the course, is to learn how to find derivatives. So let's try one more of these before you try one on your own. So again, we have a product, x to the 4th times this cube root. And so we have to use the product rule. So we're going to find the derivative of the first expression in the product, and then multiply that by the second expression in the product. And then we add the first expression in the product multiplied by the derivative of the second expression in the product. Now again, you should have these rules right in front of you, these differentiation rules. If you don't have them, you can take a picture. They're right there. Okay, so let's just double check everything. Everything looks correct. So now the derivative of x to the fourth is 4x cubed. And we can't find the derivative of this. I mean, we just can't do it because we don't know how. But if we change the form so that we have an exponential expression, now we can find the derivative. Now again, you can write a second set of parentheses there that might make it clear that you're finding the derivative of that, but the d over dx operation notation is probably good enough to show that you're finding the derivative of that. So now we can find the derivative. So I'm going really slow here. You don't have to go this slow. You can skip at least one of these steps. So the derivative of that, well, we're going to have to use the chain rule. So this is a function within a function. You have the outside function in green, and you have the inside function in blue. So you have to use the chain rule. So we're going to use the power rule to take the derivative of the outside while we keep the inside. So the green is the derivative of the outside, and the blue is where we kept the inside. Okay. And then we're going to multiply by the derivative of the inside. And the inside is 2 plus 4x squared plus x cubed. So, as you do these problems, you should constantly be checking, rechecking. Students typically don't do that, and so they make many mistakes. So just make sure that you check and recheck, because it's so easy to make a mistake, and if you make one mistake in mathematics, it throws your answer off completely. So we have x to the fourth. I'm just going to say 1/3 x to the fourth, or you can say x to the fourth over 3 times 2 plus 4x squared plus x cubed to the negative 2/3 power. And then the derivative of that expression is 8x plus 3x squared. So again, we're using the product rule, we're using the chain rule, we use the power rule, we use the constant rule in this case, we use the constant multiple rule, we actually use the sum rule because we have sums here, and so we used just about almost every rule except the quotient rule and the difference rule. I think we used every other rule. And you might ask, is this really a common type of problem? And the answer is yes. You're going to be doing these problems a lot. So we have 4x cubed times the cube root of 2 plus 4x squared plus x cubed plus 1/3 x to the fourth, and I'm going to bring this down, and I'm going to change it into the cube root of that expression squared. So I'm going very slow here. I'm going slow because I don't want to confuse students. It's very easy to just skip, 10 steps, but that doesn't really do you much good. You can skip, at least one or two of these steps. You don't necessarily have to show everything here. Okay, so the only question at this point is how can we simplify the expression? So the first expression, we can kind of just rewrite that. And then I'm going to multiply x to the fourth times all this and put it in the numerator. So we're going to have 8x to the fourth, or 8x to the fifth actually, plus 3x to the sixth. So, and then the 3 is going to go in the denominator, and then we have cube root, all of that stuff raised, cube root of all of that stuff raised to the second power. So, again, my advice to you is just go back and double check. That looks correct. So there's 3 problems where we had to use the product rule along with the chain rule. So at this point, it's time for you to try. So get a picture of these problems, and I'm also going to give you a chance to get a picture of the differentiation formulas and the exponent rules. Okay, so I want you to try number 4. We have a product of 2 expressions, and so we're going to have to use the product rule, and we also have a function within a function, so we're going to have to use the chain rule while we use the product rule. So your first thought should be, how do I use the product rule? So try number 4. When you come back, we'll do it together. Okay, we're back. So that is it. So if you got that right, excellent. Alright, so I want you to try number 5. Go and attempt number 5. We have a product, this blue expression times the green expression. And so you want to use the product rule. Try number 5. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Just be aware that if you wanted to, you could factor out this to the second power, and then you could take to the second power out of that. But you could also take x to the fifth out. But that actually, I don't know if that would really lead you to anywhere. But just be aware that sometimes they do that in textbooks and make the answer look different. So go ahead and try number 6. Remember, we can't find the derivative of this unless we change it to an exponential expression. So you can look at this problem to help you. And we're using the product rule because we have a product of the blue expression and the green expression. So if you want to find the derivative, we have to use the product rule. So go ahead and try number 6. When you come back, we'll do it together. Okay, we're back. Everything looks correct, so if you got that right, excellent. Okay, so we had to use the chain rule one time in those previous problems. We were using the product rule and we used the chain rule once. Well, now we're going to use the product rule again because we have a product of a blue expression times a green expression. But we're going to have to use the chain rule twice because we have a function inside another function, but we have a function inside another function in the other expression, so we have to use the chain rule twice. Now notice it says differentiate. This is a verb that you're going to hear from time to time, and that just means find the derivative. So we haven't used that verb in this course. Notice our formulas are called the differentiation formulas. Differentiation is obviously a noun, but if you change it to a verb, it becomes an action, in this case a command. They're commanding us to differentiate, which means find the derivative. So it's just a different way of finding, or a different way of telling people to find the derivative. So we're going to use the product rule because we have a product. So we're going to find the derivative of the first expression in the product and then multiply by the second expression in the product. Then we're going to add the first expression in the product times the derivative of the second expression in the product. So again, that's just the chain, or that's just the product rule. You might be wondering, well, how many times am I going to use a product rule? You're going to use the product rule so many times that you won't even be able to count. So here we have to use the chain rule because we have a function inside another function. So how do we use the chain rule? Remember, there's 3 steps. We find the derivative of the outside function. That's step number 1. That's the green part. Step number 2 is to keep the inside function unchanged. And then step number 3 is to multiply all that by the derivative of the inside function. So that is the derivative of all of that. And I'm going to use brackets around this whole thing. And then we have negative x plus 1 to the 5th times the derivative of that. Now, I can't find the derivative of that. I just can't do it. Because we have a root x. How do we find the derivative of root x? We don't know how to do that. So what we do is we change root x to x to the 1/2 power. Like that. You can write an extra set of parentheses around the angle if you want, but I don't really have a lot of room here, so I'm just going to leave it like that. Well, actually, I should probably just write parentheses there so it doesn't cause any confusion. You're often going to see expressions in the functions without parentheses, but it's probably best to write the parentheses. It just eliminates any potential confusion. Okay, so let's continue. So we have 5 times negative 1, or 5 times negative x plus 1 to the 4th power times the derivative of negative x plus 1, which is negative 1. And then all of that is multiplied by tangent root x plus negative x plus 1 to the 5th power. And now we're going to find the derivative. So this is a function inside a function, so we have to use the chain rule. We're going to find the derivative of the outside function. The derivative of the outside function is, well, the outside function is a tangent. tangent function. So the derivative of tangent function is secant squared. That's step number 1. But step number 2 is to keep the inside function unchanged. And then step number 3 is to multiply all that by the derivative of the inside function. So again, we had to use the chain rule twice, once here and once here. Okay, so -5 times -x plus 1 to the 4th times tangent root x. Plus -x plus 1 to the 5th power times secant squared of, and I'm just going to change that back to root x. And then the derivative of x to the 1/2 power, well, that's just going to be the power rule. And then we have 1/2 minus 1. So let's write our final answer. This is going to be x to the -1/2 power, but we're not allowed to have a negative power. It's going to be x to the -1/2 power, so we can't have a negative power, and we can't have a fraction power, so we have to bring that down. So this is going to become -x plus 1 to the 5th power times secant squared of root x all over 2 times root x. So this went down because it's negative, and it became a square root because it's when you bring it down, it becomes x to the 1/2, so that would be root x. Okay, so that is the final answer. So that's a rectangle, and I want you to try a problem that is similar to that. So I'll go ahead and try problem number 8, and when you come back, we'll do it together. Okay, we're back. So if you got that right, good. Okay, let's do this problem together. This is really the same type of problem. We have to use the chain rule twice because we have a function within a function and another function within a function. And of course we have to use the product rule because we have the product of two expressions. But we have to deal with the secant function now, and so that can be a little strange. So we find the derivative of the first expression, and we multiply that by the second expression, and then we add the first expression multiplied by the derivative of the second expression. Again, this is what you do when you have a product. We have to use the product rule. So let's find the derivative of this first expression. We have to use the chain rule. So we're going to find the derivative of the outside function while we keep the inside function. And then of course we're going to multiply by the derivative of the inside function. So again, I want to keep reminding you that you don't have to write the d over dx, you don't have to write the purple part. You can just find the derivative of the purple expression and just write it. Instead of writing this, you can just write 3. You can just jump ahead. You don't have to show that you're finding the derivative. So why am I doing that? I'm just doing that to show you how this math works. That's the point of doing this, just to show you how it works. So again, I'm going slow on purpose so you can see how this works. But if you are comfortable moving forward, then by all means go ahead and do that. You can skip at least 1 or 2 steps that you see here. So now we have to find the derivative of the secant function. And remember, the derivative of the outside function, which is the secant function, is secant times tangent. That's the derivative of the outside function. But remember, the second step is we have to keep the inside function. We don't do anything with the inside function, we keep it. But because the secant function turned into the product of 2 trigonometric functions, the inside function is actually going to appear twice. So that's what's kind of strange when you find the derivative of the secant function or the cosecant functions. And in this case, our explanation of how to use the chain rule kind of doesn't really work that well. You have to modify the explanation, but it gets a little complicated to modify the explanation, so I don't know if it's really worth it to go into that. You can consider the inside function to be the input of the derivative of the outside function, but again, that doesn't really mean much to most students. So, in order to reduce confusion, I guess I'm going to write brackets. I guess I'll just write brackets around the tangent x squared. Actually, I don't need to do that because the d over dx separates. Okay, so now let's try to simplify. The derivative of 3x minus 1 is 3. And just rewriting this, and the derivative of x squared is 2x. So now we probably should put some brackets just so we know that this is not part of the tangent function. It's just multiplied. So again, go back and double check. Don't go forward until you've double and triple checked, because you don't want to waste your time. Okay, so now we're going to multiply these 3's. So we have 9, 3x minus 1 squared. And it's best to write your trigonometric functions to the right of the product, because that reduces confusion. If you write it to the left of the function, then it seems like it's inside the secant function. That creates problems. And then we have 2x times 3x minus 1 cubed times secant x squared times tangent x squared. So there you go. That is the derivative. And so I want you to get a picture of that problem, and I want you to use it to help you with number 10. So again, we have a product, which means we have to use the product rule, but we have a function within a function, and again, a function within a function. So we have to use the chain rule twice as we use the product rule. So try number 10. When you come back, we'll do it together. Okay, we're back. And so there you go. Have you got that right? Excellent. So now we're going to use the chain rule with the quotient rule, because we have a fraction here. We're dividing one expression by another expression, so if you want to find the derivative of the resulting expression, we have to use the quotient rule. But you're going to find that as we use the quotient rule, well, we're also going to have to use the chain rule because we have a function inside another function. So the derivative, according to the quotient rule, the derivative of this expression is the derivative of the numerator of the fraction times the denominator minus the numerator of the fraction times the derivative of the denominator. And all of that is divided by the square of the denominator. So that is the quotient rule. So now all we have to do is find the derivative of each one of these expressions and simplify if we can. We may not be able to simplify very easily. So the derivative of x is obviously just 1. And the derivative here, well, we're going to have to use the chain rule. So the derivative of the outside function is cosine, because the outside function is sine. But remember, we have to keep the inside function unchanged. And then we multiply all that by the derivative of the inside function. So that was the derivative of this expression here. Then we divide all that by the square of the denominator. And we can move this 2 here so we don't have to write so many parentheses. But you don't have to move it there if that confuses you. Okay, so now we have sine of 6x to the 5th power minus minus x times cosine of 6x to the 5th power, and I'm going to have to use brackets when we find the derivative, so that purple derivative is 30x to the 4th power. And then we're dividing all that by sine squared of 6x to the 5th power. Alright, so looks like our final answer is going to be sine of 6x to the 5th power minus 30x to the 5th power times cosine of 6x to the 5th power all over sine squared of 6x to the 5th power. And I think that's as simple as we can get for the answer. There may be ways to simplify further, but it's not really even that necessary to worry about that. So we use the chain rule with the quotient rule. So we're doing two things. We're reviewing the quotient rule and the product rule, and we're also reviewing the chain rule. So let's try another one of these problems. We're dividing, we have a quotient, and so if we want to find the derivative of that expression, we have to use the quotient rule. So the quotient rule tells us to find the derivative of the numerator and multiply that by the denominator. Then subtract the numerator multiplied by the derivative of the denominator. Then we divide all of that by the square of the denominator. Again, this is the quotient rule. So let's double check all that. Everything looks correct. So now we're going to have to use the chain rule for this expression here. So find the derivative of the outside expression while we keep the inside expression, and then multiply by the derivative of the inside expression. Alright, and then we multiply all that by x to the fourth plus 10. And the derivative of x to the fourth plus 10 is 4x cubed. And all that is divided by x to the fourth plus 10 to the second power. So let's make sure that we did all this correctly. Everything looks correct. So now we have 3 times 3x plus 5 to the second power times 3. The derivative of 3x plus 5 is 3. And I'm going to go ahead and move that 4x cubed in front. It's traditional to write a monomial factor in front. And then all of that is divided by x to the fourth plus 10 squared. And then we want to multiply the 3's. So I'm going very slow here, as you can tell. You don't have to show quite so many steps. You can probably skip at least 3 steps. I mean, at least 2 steps, don't skip too many steps. Obviously you don't have to rewrite the whole thing just to combine the 3's, but I have to do that to show the process here. You don't necessarily have to do that. But remember, if you skip too many steps and you try to go back and figure out what you did wrong, it becomes a hopeless endeavor, so be careful. You have to show enough steps so that you actually know what you're doing. Okay, so at this point, I would just allow you to write that as the answer. But I just want you to be aware that textbooks will oftentimes write the answer in a different form when you're doing a problem that requires the quotient rule. What they'll often do is they'll factor out 3x plus 5 squared. From the numerator. And then they'll simplify what's left. So they'll then combine all this stuff here. Sorry, my computer's going kind of slow. So they'll get 9x to the fourth plus 90 minus 12x to the fourth minus 20x cubed, and all that is multiplied by 3x plus 5 to the second power all over x to the fourth plus 10 squared. And then they'll combine all this, and we don't really have enough room to write another step, so I'll just recombine in my head. So 9x to the fourth minus 12x to the fourth is negative 3x to the fourth. And then we can write the negative 20x cubed next. Usually our polynomials are written in descending order of powers. And then we have positive 90. But you may see the answer written in a slightly different form. You may see this negative 1 factored out, because textbooks typically don't like negatives written on coefficients if they can avoid it. So you may see it written in this form, but we don't really need brackets anymore, so we can change to parentheses. So if you write your answer in this blue form here, that's completely fine with me, but just be aware that if you're checking the back of a textbook, or in the back of the book where it shows you answers, it's almost a guarantee that your answer is going to be written in a different form. And that makes it very difficult for calculus students to check their answers, because as you can see, this form down here looks very different from this form up here. So just be aware of that. That's a huge problem for students. So try number 13. And I know what you're thinking. You're thinking, well, how do I deal with that problem? Well, all you can do is just try to change the form by factoring. Factor the numerator and see if you can come up with a different form. That's the only way to really check the answer. So I want you to get a picture of problem number 11. Also get a picture of the quotient rule. That's this green rule down here. If you forgot the quotient rule, if you don't have it in front of you, you need that. And of course we have the exponent rules. You get a picture of those if you need those. So try number 13. When you come back, we'll do it together. Okay, we're back. Okay, so if you got that answer, excellent. I pulled the green negative out in front. And be aware that some people might pull a 2x factor out of here and put it in front. So however you want to do that, it's fine. So I want you to get a picture of 12 and 13. And I want you to use those problems along with number 11 to help you with number 14. Again, we're dividing an expression by another expression. We want to find the derivative, dy over dx. So we have to use the quotient rule, and you're going to find that as you use the quotient rule, you'll also have to use the chain rule. So try number 14, and when you come back, we'll do it together. Okay, we're back. So if you didn't simplify all the way down to here, that's okay. I don't really care that much. But technically, you know, the answer should probably be written in this form, because it's just a matter of using FOIL to multiply those binomials. So if you got that right, excellent. Okay, so let's try number 15 together. Now we're finding y prime, but we have a quotient. We're dividing 4 by an expression, so we can use the quotient rule. Now we're going to learn easier ways to do this in the next class, but today we're just getting some experience with the quotient rule, and so we're just going to use the quotient rule here. So the quotient rule tells us that we can find the derivative of this expression by finding the derivative of the numerator and then multiplying that by the denominator. and then we subtract the numerator times the derivative of the denominator. Sorry, my computer's going kind of slow here. Okay, so then we divide by the square of the denominator. And again, you can use parentheses, but that seems kind of confusing, so you can also use brackets. Alright, so the derivative of 4 is obviously just 0. So that makes things kind of easy for us. And we need to use the chain rule when we find the derivative of all this. So we find the derivative of the outside function while keeping the inside function unchanged. And then we multiply by the derivative of the inside function. So derivative of the outside while we keep the inside unchanged, and then multiply by the derivative of the inside function. And all that, of course, is divided by the square of the denominator. But we're going to use exponent rule number 5. Raising a power to another power, you multiply the exponents. So obviously this expression becomes 0. And we can multiply 4 and 5 to get 20. And we have x cubed minus 4 to the 4th power, and then 3x squared. All that is over x cubed minus 4 to the 10th power. So then we have negative 60 x squared times x cubed minus 4 to the 4th power, all over x cubed minus 4 to the 10th power. Now we're not done, because we can definitely simplify this quite a bit. Notice that we have these terms here that look very similar. So we're going to use exponent rule number 2. We're simply going to subtract the powers. Or if you want to, you can write it like this. We're going to factor out x cubed minus 4 to the 4th power. So I change the denominator to that. And you can see that these cancel out. You don't have to show that. You can just do it in your head if you want to, but so we have negative 60 over x cubed minus 4 to the 6th power. And it's traditional to write the negative in front of the fraction. You don't have to do that, but it's traditional to write in that form. So I want you to get a picture of this, and I want you to try number 16. So again, we have a quotient we're dividing, and so we're going to use the quotient rule to find the derivative of y. Now, I just want you to know that it's probably best to rewrite as negative 2 over the square root of 6x minus 1. That's probably going to reduce a lot of confusion. you don't have to do it that way. You can actually use the constant multiple rule, which says that the derivative of this expression is the constant times the derivative of whatever this is. So you can just keep the negative out in front. That sounds like it would be a good idea, but probably not, because it might cause some sign problems. So go ahead and try number 16, and when you come back, we'll do it together. All right, we're back. So if you got that right, excellent. So if you had some trouble with this, that's okay. Again, you see these blue bases? They're the same, which means that we can just subtract the exponents. When we subtract the exponents, we get negative 3/2 power. And that means we have to bring it down and turn it into a positive 3/2 power. And 3/2 means the square root of whatever the base is cubed. Okay, so let's try this next problem together. We have a quotient, so we're going to find the derivative, and the derivative is the derivative of the numerator multiplied by the denominator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. So the derivative of -1 obviously is just 0. And probably should put parentheses around that. We have a double negative, so it's going to become positive. And I'm going to rewrite that expression as cosecant x squared. So we have not taken the derivative of this expression here yet. I changed the form first. So we have 0 plus, and we're going to have to use the chain rule. The derivative of 10 obviously is just 0, but the derivative of this is going to be the derivative of the outside function and then we keep the inside function unchanged, and then we multiply by the derivative of the inside function. All that, of course, is divided by the square of the denominator. Okay, so we end up with 2 times cosecant x to the first power. You don't really have to write that intermediate step. The derivative of cosecant x is negative cosecant x times cotangent x. And then we have, usually the negative is written in front of the fraction. Doesn't really matter that much, but that's typically how it's done. And we have 2 times cosecant squared x times cotangent x, or you can write the cotangent first. It doesn't really matter. That's all over the denominator squared. So that's pretty much all you can do there. A lot of students would say, well, I can just cancel these out. You can't, because we have a sum squared in the denominator. If this 10 were not here, that would be a different story. You could cancel some cosecants out, but the 10 is added, so it's not the same situation. So I want you to get a picture of that problem. And I want you to try number 18. So we have a quotient. We're dividing 8 by an expression, and we want to find the derivative of that. So this is going to be y prime. And of course you're going to have to use the quotient rule. Try number 18. When you come back, we'll do it together. Alright, we're back, and there you go. Now again, students are going to say, well, I can cancel these out, but you cannot, because the secant cube down here is part of the difference of two things. It's not a factor of the denominator. You can only cancel if you have factors that are common in the numerator and the denominator. So if you got that right, excellent. So now we're going to use the chain rule twice with these problems here. We're still going to use the quotient rule, but we're going to use the chain rule twice. And notice that the directions are to differentiate. It doesn't say find y prime or dy over dx, it just says differentiate. So what notation do we use? Well, obviously we're not going to use f prime of x because the function is not named f of x, so we can't do that. We can either use y prime or we can use dy over dx. So it's actually up to you which one we use. Y prime is probably better just because it's easier to write, but I'm going to use dy over dx. And again, we're going to have to use the chain rule twice because we have an inside function and an outside function, and an outside function and an inside function in the numerator and the denominator. So using the quotient rule, we find the derivative of the numerator, and then we multiply that by the denominator. And then we multiply the numerator and the derivative of the denominator. And it's probably good enough just to leave it like that, but if you want to, we can write some brackets there. And then we divide all that by the square of the denominator, and again, brackets may help to clarify. So let's check everything that we wrote. Looks correct. So now we have to use the chain rule here. So we're going to find the derivative of the outside function, keep the inside function, and then multiply by the derivative of the inside function. So we found the derivative of the outside function while keeping the inside function unchanged, and then we multiply by the derivative of the inside function. And all that, of course, is multiplied by x squared plus 4 cubed. And then we have to use the chain rule again because we have a function inside another function and we're finding the derivative of it. So we find the derivative of the outside function while we keep the inside function unchanged, And then of course we multiply by the derivative of the inside function. So derivative of the outside function, keep the inside function unchanged, and multiply by the derivative of the inside function. And continuing with the quotient rule, I'm going to use exponent rule number 5, which means that we can multiply these exponents to get 6, raising a power to another power. Okay, so now we can simplify. We have 2 times 3 minus 7x to the first power times negative 7. So that derivative became negative 7. And all of that times x squared plus 4 to the third power. And then we have x squared plus 4 to the second power. And 2 times negative 7 is negative 14. I'm going really slow here on purpose because we're showing every single step, just about every single step. So now you'd probably think that we're done, and we could be done, but we have common factors here. So we can factor out an x squared plus 4 to the second power in the numerator. And in the denominator, we can factor 2x squared plus 4 to the second power times x squared plus 4 to the fourth power. So I changed this to this. And in the numerator, I'm going to again factor out x squared plus 4 to the second power. So we have negative 14 times 3 minus 7x times x squared plus 4, and then minus 6x times 3 minus 7x squared. So I'll see if I can find some more room here. And we need another parenthesis, so I'm going to actually change these to brackets. So I'm going to copy all this stuff and bring it to this next page because there's quite a bit of work here that we have to do. The purpose of this is really just to use the chain rule and the quotient rule. It's not really to do a bunch of algebra, but unfortunately in the calculus curriculum you are expected to do a lot of algebra. The good news is that on the College Board exam you're never going to have to do algebra like this. You'll have to do some algebra, but it's not going to be quite this complicated. So these expressions are going to cancel out, and so you're left with, well, we can multiply these using FOIL, but it doesn't look like that's really going to do much for us. It's just going to take up our time, so looks like we can just write what we have. That's probably going to be good enough. So there you go. You could put that in, various different forms, but we don't really need to spend a lot of time with that. So there's an example where we had to use the chain rule twice. So I want you to get a picture of this problem and use it to help you with number 20. So we have a quotient of two expressions. We're going to have to use the quotient rule, and you're going to have to use the chain rule twice as you use the quotient rule. So also remember, our directions were to differentiate, so you can call this y prime, or you can call it dy over dx. It's up to you. Try number 20, and when you come back, we'll do it together. All right, we're back. So if you got that answer, excellent. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's the exponent rules. And screenshot number 1 of this class. And number 2. Number 3. 4. 5. 6. 7. 8. 9. 10. 11. And don't go before you get your homework. Remember, if you don't do the homework, it's 100% guarantee you're going to learn absolutely nothing in this entire course. The homework is not optional. So here's screenshot number 1 and number 2, number 3, number 4, and number 5, but don't go before you get the answers. Remember, if you don't check your answers, then you're just wasting your time. The homework is a complete waste of time unless you check your answers and make sure you did it correctly. If you do the homework incorrectly, it's a complete waste of time. So get that homework done completely and correctly, and I'll look forward to seeing you in the next class.